Hello student, myself Nimesh Prabhakar. Welcome to Process Control lecture series. In my previous lecture, we discussed about the control mode. Now, in this lecture, we discussed about the two position mode. So, now we start. So, two position mode. So, it is also known as on-off controller. So this is the another name of two position mode. So that means it is known as on-off controller. The most general form can be given by P is equals to 0% when error is less than 0 and P is equals to 100% when error is greater than 0. What indicates this equation? This equation indicates when error is less than 0. So at that time the controller output is 0. But when error is greater than 0, that means controller output is 100%. That's why it is known as on-off controller. That means only two position is possible. Yeah, on or off. This relation shows that when the measured value is less than the set point, full controller output results. When it is more than the set point, the controller output is 0. Now we understand what is two position controller by help of this example. How it works. So here we take the example of space heater. If the temperature drops below a set point, the heater is turned on. Now, if temperature is rise above the set point, it turns. So this is the simple two position controller operation. Now we understand natural zone. So what is natural zone? We understand. If particle implementation of the two position controller, there is an overlap as if we increase through 0 or decrease to 0. In this path, no change in the controller output occurs, which is illustrated in the figure. It can be observed that until an increasing error change by delta EP above 0, the controller output will not change state. In decreasing, it must fall delta EP below 0 before the controller change to 0%. So the range to delta EP is referred to as natural zone or the differential gap. Now, what are the applications of two position controller? Now we discuss. So generally the two position control mode is best adapted to large scale system with relatively slow process rate. That means we can use two position control mode in a room heating system and also air conditioning system. Moreover, we can also use two position control mode in system in which large scale changes are not common. That means we can use two position control mode in liquid bar temperature control system and level control in a large volume tank. So these are the application of control mode. Now we understand by help of one example. A liquid level control system linearly converts a displacement of 2 to 3 meter into a 4 to 20 milliampere control signal. A relay serves as two position controller to open and close the inlet valve. The relay closed at 12 milliampere and open at 10 milliampere. And find relation between displacement level and current and neutral zone or displacement gap in a meter. So here we have to find the relation between the displacement level and the current. And second, we have to find the neutral zone. So here we have given liquid range is between 2 to 3 meter. So that means H minimum is equals to 2 meter and H maximum, that means, is equals to 3 meter. H indicates the height. And control signal range is between 4 to 20 milliampere. That means I minimum is equals to 4 milliampere and I maximum is equals to 20 milliampere. Now we start. The linear relation between the level and control current is given by H is equals to K into I plus H0. So the simultaneous equation for the above range are: for low range signal, 2 meter is equals to 4 milliampere plus H0, and same as we can write for the high range signal is 3 meter is equals to K into 20 milliampere plus H0. Now we are solving this equation. So we get K is equals to 0.0625 and H0 is equals to 1.75. So therefore, the relation between displacement level H and current I is given by H is equals to 0.625 plus 1.75. Now we have to find the relay closed. Now we start the procedure for the second one. The relay closed at 12 milliampere, which is high level, that means HS. So HS is equal to 0.625 into 12 plus 1.75. So we get HS is equal to 2.5 meter, that means highest height. And same as we get the relay open at 12 milliampere, which is low level HL. So we can find this is by your HL is equal to 0.0625 into 12 plus 1.75. So we get HL is equal to 2.375 meter. Therefore, the natural zone is HH minus HL. So we get natural zone is equal to 0.125 meter. Now we understand by help of second order example. So here we have given the temperature of water in the tank is controlled by the two position controller. When the heater is off, the temperature drops at 2 Kelvin per minute. When the heater is on, the temperature rises at 4 Kelvin per minute. The set point is 323 Kelvin and the natural zone is 4% of the set point. There is a 0.5 minute lag at the both on and off switch point. Find the period of the oscillation and plot the water temperature versus time graph. So here we have given temperature drop is equal to 2 Kelvin per minute, temperature rise is equal to 4 Kelvin per minute, and control lag is equal to 0.5 minute, and natural zone is equal to plus or minus 4%. That means here natural zone is given in the percentage and the set point is 323 Kelvin. So now we solve this example. So the natural zone in temperature is delta T is equal to plus or minus 4% of set point, that means 323 Kelvin, So we get natural zone is equals to 13 Kelvin. Therefore, the temperature will vary from 310 to 336 Kelvin. That means if we subtract 13 from 323, so we get 310 and we add 323 plus 13, so we get the 336. That means highest limit of the temperature. Initially we set the set point value. The temperature will drop linearly, which can be expressed by T1T is equals to Ts minus 2T minus Ts, where the Ts is the time at which we start the observation. Tts is the temperature when we start observation is 323. The temperature will drop 4% of set point 323, which is 310 Kelvin. Time taken by the system to drop temperature value is 310 Kelvin. So 310 is equal to 323 minus 2 T minus 0. So we get T is equal to 6.5 minutes. Understood, due to controller lag is equal to control lag into drop rate. So here control lag is a 0.5 minute into drop rate is a 2 Kelvin per minute. So we get 1 Kelvin. Understood. So due to control lag, temperature will be reached 309 instead of 310. You can see in the graph 309. Now, from this point, the temperature will rise at 4 Kelvin linearly till 4% of set point. That means 366 Kelvin, which can be expressed by T2T is equal to TTH plus 2T minus TH, where the TH is the time at which temperature goes on. TTH is the temperature at which heater goes on. 336 is equal to 310 minus 1 plus 4 T minus 6.5 plus 0.5. So we get T is equal to 13.75 minutes. Overshoot due to control lag, we can find out by using control lag into rise rate. So we know control lag is the 0.5 minute and the rise time is the 4 Kelvin per minute. So we get 2 Kelvin. So due to control lag, temperature will reach 338 instead of 336. So the oscillation period is, we can calculate as 13.75 plus 0.5 plus 0.5 control lag plus 6.5. So we get oscillation is 21.25, or we can say 21.5 minutes. So in this lecture we discussed two position mode.